Today we're going to begin with our notes in the Chapter 10 section on changes of state and phase diagrams. We want to start by looking at evaporation and condensation. So the image on the right is showing us a liquid in a flask that is evaporating, right? Meaning that the liquid phase is turning into a gaseous phase. And the second flask is sometime later when the liquid is still turning into a gas, evaporation is still taking place, but also some of the gas particles are now turning into a liquid. So condensation is taking place. And then finally, at the latest time, the rate of evaporation is equal to the rate of condensation. This point is referred to as the vapor pressure. So in a closed container, the rates of vaporization and condensation for a substance will become equal. The gas pressure when this occurs is called the vapor pressure. This graph on the left, we just want to practice reading. So over a period of time, just like our three flasks occurred over a period of time, we take a look at the rate and we see that the rate of condensation slowly increases as there's more gas in the air, but the rate of evaporation stays consistent. And when the two are equal, that's when we reach the scenario in flask C. That's when the pressure inside the flask is called vapor pressure. And so when vapor pressure is low, then that means that there's mostly evaporation. It's relatively easy to evaporate because there's very little pressure pushing down. And then when vapor pressure is high, so when vapor pressure is high, then that means there's a high amount of pressure pushing down. It's equal to the pressure pushing up, and it's difficult to evaporate the liquid, right, because there's so much condensation pushing back down on it. So low and high vapor pressure are two concepts we want to think of. Low, high on the spectrum. Vaporization is an endothermic process, right? Endo meaning energy, in, thermic meaning thermal energy or heat energy, and energy absorbed is called heat of vaporization. This is the symbol for heat of vaporization. We won't be using it to do any math right now, but it's kind of interesting to think about it this way. This is the amount of energy required to vaporize.
Right, that's to turn from a liquid into a vapor. 1 mole at 1 atmosphere. So
1 mole of a substance at 1 atmosphere of pressure. So this is the amount, 1 mole at 1 atmosphere of pressure. So it takes energy. That's the most important part, right? It's endothermic. So generally when you heat a liquid that's sitting in an open container, that liquid, mole by mole, quantity by quantity, turns into a vapor, but that does depend on the pressure that's pushing down on it. 1 atmosphere is sort of the typical pressure at sea level, which is approximately where we live. If we lived on a mountain, pressure would be lower. If we lived in a valley, pressure would be higher. But we typically think about 1 atmosphere as being normal at sea level. Now, why is it endothermic? It's endothermic because of the forces between the molecules. Remember, we call those intermolecular. The intermolecular forces of a liquid must be overcome. So it takes energy to break those particles apart, right? If you ever made a particle diagram of something evaporating, you start out with particles of liquid. They're relatively close together, but then as they absorb energy, those particles become more and more excited. They can move more, and eventually they can escape, and the gaseous particles have more space in between them. That's because they absorbed energy. Endothermic is the word we use for energy in. Strong intermolecular forces will result in fewer molecules able to enter the gaseous state. So it would be very difficult to turn into a gas something that has the electrostatic forces that exist between ionic structures. It would be take less energy to separate polar covalent molecules that have dipole-dipole forces or London dispersion forces. And lower vapor pressure. So here's kind of an example of a vapor pressure. This first is a standard vacuum. That means that there are no gases inside, and then the tube is filled with mercury. So all of this is mercury, and the dish has mercury in it too. And then the outer dish is open to the atmosphere. So what we have is the atmosphere pushing down. That's the pressure from the atmosphere. And then just nothing pushing here. So this pressure is that of a vacuum, right? And the two are at equilibrium, and 760 torr is equal to 1 atmosphere. Those are the same value. Now, what if that space that were filled with nothing is now filled with water vapor, the pressure of H2O gas pushing down, and is still pushing against the same atmosphere? Well, you can see that the vapor pressure of water is higher than the vapor pressure of no particles at all. And that makes sense, right? Because there are particles of water here, and those particles will be bouncing and pushing and exerting a force down and confining the mercury into this space. And so the pressure from the atmosphere able to push on the water is less, right? Because the water is actually pushing back. So you've got pushes in two directions. So if there's nothing there and the atmosphere is able to push up to a maximum of 760 torr, remember that's 1 atmosphere, then when we have water there, now the atmosphere is only able to push 736 because the water is also pushing back. What if the vapor then was ethanol? Pushing down. And you can see the atmosphere is also playing its same role. Then you can see that the ethanol takes up even more space. That means that the vapor pressure of ethanol is even higher than that of water. In fact, we're calculating the vapor pressure up above. The atmosphere minus the pushback is the vapor pressure of water. The atmosphere minus the pushback of ethanol is the vapor pressure for ethanol. And then finally, this is ether. So the vapor pressure for ether is very, very great. So substances that have a relatively low vapor pressure and a relatively high vapor pressure are being demonstrated in this image. Lower intermolecular forces give substances a higher vapor pressure. Ether has a high vapor pressure, which means it has low intermolecular forces. And what are those again? Those are the forces that hold the particles of ether together. So ether readily evaporates. The particles of ether are not being held together strongly. They readily separate into a gas, and so that gas exerts a very high pressure. So low intermolecular forces is associated with high vapor pressure. We would say that those substances are more volatile. So these are just some standard vapor pressures we can see for water, and you can see that when water is cold, its vapor pressure is relatively low. When water is at room temperature, its vapor pressure gets high, right? Doesn't water tend to evaporate more at room temperature than when it is cold? And if you heat water, its vapor pressure becomes very high. So when you increase the temperature of a substance, such as water, then you make more vapor. You're putting in more energy, so you're more able to separate those particles into a vapor, and you're more able to overwhelm those forces in between the particles. This is just another graph showing us similar data on that relationship between temperature and the movement of the particles. The graph on the left shows us T1, that's a low temperature, and the graph on the right shows us T2, that's a high temperature. And on the x-axis, you see we have kinetic energy, so the energy of motion. And then on the y-axis, we have number of molecules with that energy. More particles can be separated at a high temperature than at a low temperature. That's what it says here. At higher temperatures, a greater percentage of the molecules in the sample have the kinetic energy needed to overcome the liquid state's intermolecular forces. More molecules become a gas. Pressure at higher temperature. For any substance, a higher vapor pressure is found at higher temperatures. For any temperature, a higher vapor pressure is found in substances with weaker intermolecular forces. So this is something that we're seeing here. We've got temperature on the x-axis and vapor pressure on the y-axis. And as we increase the temperature, we see the vapor pressure gets higher. There's a little bit more of a lag time for water and a little bit more of a lag time for ethanol, but the relationship for the diethyl ether is very direct. And at, again, sea level, and that's 1 atmosphere or 760 torr, water's vapor pressure, the temperature at which it becomes a gas, is 100 degrees Celsius. Ethanol's is 74, and ethers is only 34. So which one of these three is most difficult to turn into a vapor? Water. It's difficult to turn water into a vapor because it requires a 100-degree temperature increase. Ethanol only requires a 74-degree temperature increase. Ether requires a 34-degree temperature increase. So what we're going to have to do is essentially read these phase diagrams. Pretty fun. They have temperature on the bottom, pressure on the side. They show the three phases of a substance: solid, liquid, and gas. And the temperature and pressure at which solid, liquid, and gas states are in equilibrium is blank. All three are in equilibrium at spot A. This is called the triple point. The temperature and pressure at which liquid and gas states become indistinguishable is part C. That's called the critical point. The critical point. The critical point. This is referred to as supercritical fluid. You can think of it as plasma. So here's a sample question for the ones that we'll do for homework. What process occurs as a sample of this substance at 1 atmosphere, so we'll find 1 atmosphere, is heated from negative 100 degrees Celsius to negative 60 degrees Celsius. So on this schematic, negative 100 might be right here, and negative 60 might be right here. Okay, so we've got like negative 100 approximately, negative 60 approximately, and this is 1 atmosphere. So the range we're talking about is from here to here. What process occurs? Well, when a substance goes from a solid to a gas directly, that is called sublimation. You could just say it goes from a solid to a gas. The vocabulary word is sublimation. How about if it's pressurized from 6 atmospheres to 75 at negative 55 degrees Celsius? All right, let's do this one. First, we'll find negative 55 degrees Celsius. So that would be like right here, negative 55. And it's pressurized from 6, so that might be right here, to 75. And that might be right here. Actually, I'm starting to think this is probably going to be a little bit over like that, right? Because 55 is right there next to 56. So what happens? Well, it starts out as a liquid, and then it crosses the line and becomes a solid. So liquid to solid, that's called freezing. By the way, did you realize that just by increasing the pressure on something, you can cause that substance to potentially change phase? You can cause it to freeze. That's what we've done here. Usually we think about changing the temperature, but temperature and pressure both impact the amount of energy that molecules have, how free they are to move, how free they are to separate into a vapor, or how confined they are to stay limited into the liquid or solid state.